Okay, everybody. When is a sequence called Cauchy? Part A. The sequence, let's call it Z sub n, is Cauchy. Now here's the definition. When, for all D, there exists a cutoff such that whenever you have any pair of indices past that cutoff, the corresponding sequence elements are D close to each other. Okay, let's fill this in. For any desired amount of closeness, little d, there exists a cutoff index such that any pair of indices past that point, the corresponding sequence elements are within D of each other. In other words, you zoom in and eventually, past n, all the sequence elements are very, very close to each other. That is Cauchy, okay? Prove that every convergent sequence is Cauchy. So let Cn converge to some limit. So let's give that some limit C. Okay. Let the sequence Cn converge to some limit C. And we need to prove that C sub n is Cauchy. That's what we want to prove. Okay, so let D be given. We need to find a capital N. We need to find a capital N such that when m and n are past n, that implies that the Cn minus the Cm are less than D. Okay, so where will we find this capital N? Well, we assumed that the Cn converged to C. Now, let D be given. Then, since the C sub n converged to C, there exists n such that what? Maybe when we go past that point, then the Cn and the C are less than D over 2 away from each other. Okay, so let's picture this. Here's my limit C. It's somewhere in the complex plane, and then here's Cn, and maybe here's Cm. And now I want these to be D close to each other. I can make this D over 2, and I can make this D over 2. This distance then, is that going to be less than D? Well, yeah, I think so, because if these are both within less than D over 2, maybe I better make them smaller. Yeah, okay, so this is going to work because if I'm at the limit C and I put some ball of radius D over 2, then if C sub n is within that D over 2 and C sub m are within D over 2, then their distance is less than D, because the diameter of this ball, the diameter of the ball is D. And so if both of these things are inside the ball, then they're within D of each other. So this is going to work. This is going to work. Okay. So, okay. Now, why can I put Cn and Cm? So if m is greater than n, that implies that Cm minus C is less than D over 2. So basically, because this sequence converges, I can choose the value d over 2, and there must exist an n. Okay? But then, if both little m and little n are past that point, that implies that the Cn minus Cm is less than d, since they are both inside a ball of diameter d, about or centered at C, the limiting value. In other words, I just described this picture. Okay. So let me see if this truly worked. Let Cn converge to some limit. We need to prove that this sequence is Cauchy. Okay, so let D be given, and we need to find an n such that going past that puts these within D. Well, because the C sub n's converge to some limit C, then there does exist the capital N that puts the C sub n's and C within D over 2 of each other. And then, if we're both past that point, then these two are less than D by this, essentially this picture slash this, these words. Okay. So that proves that every convergent sequence is in fact a Cauchy sequence. Okay. You can have Cauchy sequences in the rational numbers that do not converge, but the construction of the real numbers, and hence the complex numbers, which are just two copies, both of these are complete, and what that means is that Cauchy sequences will also converge. We will use that later. Okay, but this sort of had nothing, well, it doesn't have, it's definitely relevant, it's just not part of the actual problem. So here is where the problem ends, and my proof isn't over.